Hi everyone, welcome back after the break. We are now going to be moving on to systems of linear equations and talking about how we can use matrices to help solve them. So this is lecture 3B of MATA35. So let's go ahead and get started, and we'll get started by reminding you of the rabbit population question, which we just ended with. So we had a Leslie matrix times a population vector, and that gives you the population vector for the next year. But now, suppose that our problem is slightly different. So this lets you evolve the system forward. So if you have you know what the population is in year 1, this tells you what the population is in year 2. But suppose you're trying to go backwards. Suppose you have a Leslie matrix and the population vector for year 2. Now, what was the population in year 1? Now, we know the answer to this one, since this is exactly the thing we did earlier. But one of you was asking the question, well, do you always get year 1? And no, you don't. You only get year 1 when you're evolving the population forward, but not when you're figuring out what the population was previously. And now, there are a couple of different ways of solving this, and yes, we have a question by Samantha. Can you divide matrices? The answer to that is complicated, but the answer is sort of. We're not going to get to that in this lecture. We're going to give a different method. But yes, there will be an idea of a matrix inverse, which is basically the same as dividing by a matrix. It doesn't always exist, so you can only divide by some matrices and not by other matrices. And this will come up in the next, on Friday, basically. We won't get to it today. We're going to give you a different method, and then we're going to sort of lead you into like this idea of dividing by matrices. But the first thing, one thing you can do is, well, you can turn it into a system of equations, right? So what we had here was, well, we had our Leslie matrix times a population vector. So 2, 3, 0.5, 0.9. We don't know what this is, so we're going to just give it variables. So when you don't know what the answer is, you just give it some variable names. Let's call this x and y. And we know that this is equal to 230, 59, right? And so x and y are arbitrary. And let's see, this here is L, this here is P2, which we know, and this here is, we're going to call this P1, and we don't know what P1 is. But let's multiply the matrices out now. And it turns out that when we do that, we'll end up with a system of equations, which you guys may remember from your algebra classes. So you end up with 2x plus 3y is equal to 230. Because when you multiply out the left side, the first entry there is 2x plus 3y. And the second entry is 0.5x plus 0.9y is equal to 59. Okay? So all we're doing here is we're multiplying out the left matrix by that vector, and you end up with a new vector. And if you want the two vectors to be equal, each of the entries has to be equal. And so you end up with this system of equations. Now, there are many different ways of solving systems of equations, some of which you guys probably already know. Here, we're going to do something relatively easy, which is I'm going to multiply that entire equation by 4. So this is going to remain an equivalent system because you are allowed to do that. And so then what you're going to end up with is 2x plus 3y is equal to 230, and 2x plus 3.6y is equal to 236. And then what we're going to do is you're just going to subtract one system equation from the other, and that's going to give us minus 0.6y is equal to minus 6, and so therefore y is equal to 10. And therefore x is equal to 100 by substituting back in. And this together allows us to figure out that, well, we can plug those numbers back in, so 2, 0.5, 0.9. Wait, sorry, that was a 10 there, not a 0. I think I just put the 1 too close. I multiplied by 4 so that the amount of x in both the first and the second equations were the same, so that you can subtract out. And so let's see, this is 100, and this here is 10, which we already know, and this is equal to 230, 59, which you can double check. So because you can write this as a system of equations, and we know how to solve systems of simultaneous equations, we can therefore back solve for the value of the population in year 1. And so now let's take a brief interlude and think about these linear equations. And basically what we end up with is we end up with these two linear equations from this sort of matrix equation. So we had a matrix equation, we turned it into a system of linear equations, and now we can think about like what that looks like in 2D, at least for two variable equations. Come on, there. So we can visualize two variable equations as lines, right? So if you have a let's say you had some ax plus by is equal to c, because those are our two variable equations, right? This implies that y is equal to, well, c minus ax over b, which is just equal to c over b, which is the y-intercept, minus a over b x, where minus a over b is the slope. And so, I mean, you guys have had experience graphing these things out, I'm sure. And so this ends up looking something like this, where this point here is c over b, and the slope is equal to minus a over b. But the exact details don't really matter so much. The point is that you can think of these two variable equations as defining a line in the xy plane. And it turns out that, well, any point on this line, any point on this line is a solution to the equation. So, for example, if we had a very specific equation, let's say we had x plus 2y is equal to 3, or y is equal to 3 halves minus 1 half x. Both of those are equivalent. Well, you know that x equal to 0, y equal to 3 halves is a solution. X equal to 1, y equal to 1 is also a solution. X equal to 2, y equals to 1 half is a solution, etc. So any of these solves your single equation. But now what happens if you have two linear equations, if you have multiple ones? So a solution to a system of 2D linear equations with two variables has to be a solution to both equations. That is, it has to lie on both lines. And there are a couple, so there are several different possibilities for this. So let's say we had a1x plus b1y, y is equal to c1, and a2x plus b2y is equal to c2. So you have two different equations. They both define different lines in your space. And there are a couple different possibilities. One of them, and this is the most common situation, is the two lines intersect, right? So if the two lines intersect, then your solution is at this intersection point, and so you end up with one solution. Sometimes you get unlucky, and the two lines are parallel to each other. And if the two lines are parallel, then there are no solutions. Let's see. And lastly, sometimes you have an infinite number of solutions. So if the two lines are right on top of each other. Sorry, let me make it thicker so that you guys can see even after I draw the green line through it. Sometimes the two lines are right on top of each other, and then that means you have infinite solutions. Then is our solution correct if there are multiple other answers? Well, it really depends. So, like, if you've solved your system of equations, then you will generally get a correct solution. Sometimes there will be multiple correct solutions, and you have to deal with that as well. And there are some rules for figuring out how many solutions you have. And so there are a couple different descriptions that are important here. So we're going to talk about things called consistency and dependency. So a system of equations is consistent if it has at least one solution. Another typo. That should be one solution, not one solutions. If it's inconsistent, yeah. If we'll go through this again in a moment. I'll answer your question in a moment, Sam. So if it's inconsistent, there are no solutions. So sometimes there aren't any solutions because they don't cross. If they cross at exactly one point, you have one solution. If they cross if the two lines are right on top of each other, then you have infinite solutions. So now, so this is consistency and inconsistency. If it's consistent, it has at least one solution. And then you also have this idea of dependency. So a system of equations is dependent if you can derive one of the equations from the other equations. Otherwise, the system is independent. And sometimes you'll also say that an equation in a system is dependent or independent if it has the same properties. So let's see what this means in practice. So let's go back to our example again of several different things. So sometimes you'll have two, actually, let me actually draw specific lines. So let's say we had y is equal to minus 1 half x, and we had y is equal to x plus 1. So x plus 1 is this line here, and minus 1/2 x is this line here. So this has one solution, and it is consistent because it has at least one solution, and it's independent. Because you can't get one of your equations from the earlier one by just multiplying or adding. Let's try another one. So this one's going to be easy. I'm going to say y is equal to 4, and y is equal to minus 1. So minus 1 and 4. So these are both equations, and these are in the... actually, let me... Yeah, so this is y is equal to 4, and this is inconsistent because there are no solutions, and independent. Because you can't multiply the entire equation and get the other equation. If you multiply, let's say, the y equals minus 1 by minus 4, you get minus 4, y is equal to 4, which is not the same equation. And lastly, let me give an example of dependent equations. So let's say that one of our graphs was 2y is equal to 2x plus 2, and the other one was y is equal to x plus 1. So now if you multiply this entire thing by 2, you end up getting that. And so these are dependent equations. And it turns out that when you write out the graphs of both of them, they both lie right on top of each other. So this is consistent and dependent. Oh, so because I haven't exactly defined derive, but the basic idea is can you add together or multiply equations with each other to get the other equation? So here, if you multiply this entire thing times minus 4, what you end up getting is minus 4y is equal to 4. You don't get y is equal to 4. And so this is not actually dependent. Proving that, could it be inconsistent and dependent? Ah, yes. So if you only have two equations, and is it only dependent if there are infinite solutions? No. So here we only have two equations. So if you only have two lines, many of these things are true. So you can't be inconsistent and dependent if you only have two lines. But you can be inconsistent and dependent if you have more than two lines. And is it only dependent if there are infinite solutions? No, you can be dependent and inconsistent, as I was saying, if you have more than two lines. So, for example, if you had... It turns out, and I'm not going to prove this right now, but if you had 3 lines like this, that is dependent, and it's complicated to figure out why it's dependent. That takes a little bit more work. And it turns out that there are no solutions. So it's dependent, and there are no solutions because you need all 3 of the lines to intersect. So this here would be dependent and inconsistent. But for 2 lines, you don't end up with that sort of behavior. So I'm going to ask you to try it out now. Let me reset. Just a moment. Let me reset here. And I'm going to ask you if it's consistent and independent, consistent and inconsistent and independent, consistent and dependent, or inconsistent and dependent for each of these. So the first one here, x plus 2y is equal to 5, and x minus 2y is equal to 1. So the question... Okay, so we've started getting some responses. We have 1A, a couple A's. Okay, yeah. So it turns out if you graph these 2 lines, they intersect. And so that means they're consistent because they have a solution. And they're independent because the 2 lines, you can't multiply one of the equations and get the other one. So A here is the correct answer. Okay, so now let's try out another one. So if we have x plus 2y is equal to 5 and x plus 2y is equal to 1. So the first question is this consistent? And the second question is this independent? Okay, so we've started getting some replies. Mostly B's, it looks like. Let me wait until the graph updates. Okay, yeah, so that's correct. This is inconsistent and independent. So this one here was A, this one here is B. And the reason for this is because no matter what, x plus 2y can't simultaneously be equal to 1 and 5. But at the same time, you can't multiply one of the equations and get the other one. Note that there are other ways you can be dependent instead of just multiplying, but with two equations, that's the only way you can be dependent. Okay, let's try one more. Or actually, we have two more, so let's try this one here. Okay, it looks like some of you guys have already noticed the pattern, and yes, this one is indeed consistent and dependent. And it's because if you multiply the first equation by minus 3, you get the second one. Okay, and let me reset again, and we have one last one. So notice that I have 3 variables here, so I now have made things complicated. So what do you guys think this is? Okay, yeah, so a lot of you guys are guessing D. This is the correct answer. And this one's a little bit harder to see, but you'll notice that if you take this thing times 2, you get this one. So those two are clearly dependent. And so, but at the same time, these are inconsistent because you can't have the entire thing be equal to 5 and the entire thing be equal to 10 at the same time. So that's impossible, and so it's inconsistent and dependent. Note that, so these are a couple examples of inconsistency and dependency. I should give you one more example of dependent equations. Let's say I had x is equal to 0, y is equal to 0, and x plus y is equal to 0. So this here is actually dependent. Just for the record. Because you can add these two equations together. Because if you add these two equations together, you get the third equation. So these are actually dependent equations. So this entire system is a dependent equation. So it's not just multiplying, you can also add together equations. We just didn't see any examples of that, and I thought it was important to show you one. Okay, so you guys are pretty good with that. So let's talk about some more properties of systems of equations. So there are several different ways you can think about systems of equations and variables. One of the ways I like to think about it in terms of sort of physicsy interpretation is thinking about each variable as a degree of freedom. So, for example, if you have two different variables, x and y, well, that means that you could have any solution anywhere on the xy plane. If you, as you said, you have two variables and they don't give you any constraints. On the other hand, if you have x, y, and z, well, you could have any solution that's in x, y, that's in 3 space, basically. So each variable is a sort of a degree of freedom. And each independent equation constrains the system and removes the degree of freedom. So if you think about it, you have a two-dimensional degree of freedom when you have x, y, right? But now, if you say that all the solutions lie on some line, then all of a sudden you've decreased it down to 1 dimension. It's a one-dimensional line. And if you do this again, if you do, let me use a different color. If you do this again, you've reduced the degrees of freedom again. So each independent equation reduces the degrees of freedom again, and then you have a zero-dimensional solution, which is just 1 point. So each independent equation constrains the system and removes the degree of freedom. And you can also see this, it's a bit harder to see in 3D, but it turns out that when you have an equation, just a single linear equation in 3D, you end up with a hyperplane. So you end up with something that looks like a plane in 3 space. So something like that. And then what happens is, if you have another plane, you end up constraining the solutions to lie on the line. And so this is a little bit harder to visualize because visualizing higher dimensions is harder, but you can think of each equation as removing a degree of freedom. And so this has some nice consequences, one of which is that if you have a system of n linear equations with n variables that has exactly one solution if and only if the system is independent and consistent. So obviously you can have your system be inconsistent, in which case you don't have a solution. But if it's independent, which means you don't end up having lines on top of each other, basically, or that sort of idea, lines that are almost fall on top of each other, then you have exactly one solution. And so let's give a quick example. So let's say x plus y is equal to 1, x minus y is equal to 5. So then 2x is equal to 6, x is equal, by adding the two equations together, x is equal to 3, and y is equal to minus 2. If m is greater than n, if you have more equations than variables, then this actually doesn't have a solution if all the equations are independent. And we can see this because, let's see, let's suppose we have three equations, x plus y is equal to 1, x minus y is equal to 5, and 2x plus y is equal to 0. So these all turn out to be independent. I'm not going to prove that here. But we know already that the first two, you have x is equal to 3 and y is equal to minus 2. But then when you plug that into the last thing, that implies that 6 minus 2 is equal to 0, which is not true. And so this doesn't have a solution. So you have too many constraints and not enough degrees of freedom. Lastly, if you go the other way, then a system with m linear equations and n variables where m is less than n, this has infinitely many solutions if the system is independent and consistent. Now, of course, a system with at least two equations can be inconsistent, but that's not actually, but we're going to assume that they are independent and consistent. So the easiest example is x plus y is equal to 1. You have two variables, you only have one constraint, it's just the line, and you have infinitely many solutions. Okay, so these are a couple of rules of thumb. And note that these require the equations to be independent. They basically have to be real constraints. Because if you have just two copies of the same equation, that's not going to do anything. But that's sort of the intuition behind these ideas of how many equations you need for how many variables. And so now let's actually go to solving these systems of equations. There are several different methods. And the first one you guys have probably learned before, and so a lot of this ought to be reviewed. But one is the substitution method. So you solve for a variable in one equation in terms of the other variables, and then substitute it in. And you iterate until you know the value of one variable, plug that variable into all equations, and repeat the entire process with fewer variables. So let's give an, iterate, plug, yeah. Let's give an example of this. And this is just going to be, let's say, 3x minus 2y is equal to 1, and minus x plus y is equal to 1. So if we rearrange this, this is equal to y is equal to x plus 1. We then plug that in to the first equation, and you get 3x minus 2 times x plus 1 is equal to 1. And so 3x minus 2x minus 2 is equal to 1. And so this x is equal to 3. And when you plug that back in, you get y is equal to 4. Now if we draw this out, you can also think of this in terms of the lines, and so let's say this is 1, 2, 3, 4, 5, 6. That's 4, 1, 2, 3, 4, 5, 6. So that's 4 there. And you have two equations. One of them is going to be y is equal to 3 halves x minus 1 half. So you're going to start at minus 1 half, and you're going to go up by 3 halves. So rise over run, and let's see, 3 halves. And 3 and then 4, 3 halves, and so on. And then the other one is going to be, once you put that in blue, y is equal to x plus 1, which is easy because there's your y-intercept, and your points are here. So you have your intersection point here at x is equal to 3, y is equal to 4. Okay, so that's one way of doing it. But of course, that can get a little bit cumbersome at times. And so often, one of the other things we learn is we can transform a system into an equivalent system using 3 types of operations. And so these are the types of operations we mean when you're saying that one equation can be derived from all the other ones. You can change the equivalent system by just permuting the order of the equations. That obviously doesn't make a difference. So something like x plus y is equal to 1 and x minus y is equal to 0. This is obviously equivalent to x minus y is equal to 0 and x plus y is equal to 1. so this obviously doesn't change things. You can multiply an equation by a non-zero constant. So x plus y is equal to 1 is equivalent to 2x plus 2y is equal to 2. And you can add a multiple of one equation to another one. So if you had a system x plus y is equal to 1 and x minus y is equal to 0, you can change this to a different system, x plus y is equal to 1. If you add the first equation to the second one, you get 2x is equal to 1. Now the goal is to eliminate variables, and then you can use back substitution. So once you've eliminated variables, then you can plug the variables back in, and then you can solve it. So for example, here in this equation, we've already done most of the work. It turns out that if 2x is equal to 1, then x is equal to 1/2, and 1/2 plus y is equal to 1 implies that y is equal to 1/2. So that allows you to solve this system. Lastly, you might be asking, why do we have this big interlude into the system's equations? Other way. Turns out that you can encode all this information into a matrix and then solve it using a process called Gaussian elimination, which we'll get to in a moment. So let's give an example of how you can encode this as a matrix. So let's say we had 3x minus 2y is equal to 1. Let me get the right thing here. 1, and we had minus x plus y. And we have minus x plus y is equal to 1. Okay, so now if we want to solve this, well, what can we do? We can multiply this by multiply this by minus 1, and then we get a new system, which is 3x minus 2y is equal to 1, and x minus y is equal to minus 1. You could swap these if you want. And let's do that, and you get an equivalent system. X minus y is equal to minus 1, and 3x minus 2y is equal to 1. And then what we're going to do is we're going to add minus 3 times the first one to the second equation. And that's going to give us, the first equation remains unchanged. The second equation is going to turn into y is equal to 4. And then you can substitute this back. So back substitution. And you end up with a new system, which is easy to understand. X is equal to 3, and y is equal to 4. Now, sometimes you might want to write this as a matrix. So you should recall that this is equal to, this system here, you can rewrite as 3 minus 2 minus 1, 1 times xy is equal to 1, 1. Now, we don't want to, for the augmented matrix, we're not going to actually keep track of all of that. We're just going to keep track of 2 of the pieces. We're just going to keep track of lat and lat. And so the augmented matrix is going to look like 3 minus 2 minus 1, minus 1, 1, and 1, 1. Because we're keeping track of just all the non-xy variables, since that stays the same. And then we can do the exact same operations. Oh, yeah, well, I'm about to do the exact same thing twice, so hopefully this will make a bit more sense. We can do the same operations. So the first one is we're going to take negative of row 2. So if we multiply row 2 by negative 1, what we're going to end up with is row 1 is unchanged, and you get 1 minus 1 minus 1 here. And notice that it corresponds precisely to the system of equations we had on the left. We can do this again. Here, this is row 1 is going to swap with row 2. So if row 1 swaps with row 2, then you end up getting 1 minus 1 minus 1, and 3 minus 2, 1. And, well, let's do the same thing. So let's take, so this is a slightly more complicated operation. We're going to take row 2 is going to be set equal to row 2 minus 3 times row 1. So row 1 doesn't change, but row 2, this minus 3 times row 1, 3 minus 3 is 0. Minus 2 minus minus 3 is going to be 1, and this here 1 minus minus 3 is going to be 4. And then we can do a final operation where we do this back substitution. So row 1 is going to be row 1 plus row 2. And you end up with a matrix 1, 0, 0, 1, and this is going to be 3 and 4. Okay, so everything that you can do with this basic changing things around in your system of equations, you can do in this matrix form. And it turns out that encoding this into the matrix form allows you to do this very algorithmically. So you can follow a particular procedure and you'll always get to the answer. Well, if there is an answer. And so this brings us to elementary row operations. So these are the exact same operations. Oh, sorry, that was probably too fast. Let me leave it on this page for a moment. But so basically, you can do the exact same things on these systems of equations. You can change the order of the equations. You can multiply an equation by a non-zero constant, and you can add a multiple of one equation to another. And this allows you to convert into equivalent systems to make it easier to solve. You can do the exact same thing in the sort of matrix view. You just have to do a little bit less writing since you don't have to write down all the x's and y's, and it also allows you to be more systematic with it. And so you end up with the elementary row operations, which are basically the same as your operations on your equations. And the three operations are called swap, just switching one row with another, scale, multiplying a row by a non-zero constant, and pivot, where you add a multiple of one row to another row. And if two matrices can be converted to one another via elementary row operations, they are called row equivalent. So minus 3, oh sorry, so in the previous example we had 3 minus 2 minus 1, 1, 1, 1, and that is equivalent. So this is row equivalent to 1, 0, 0, 1, 3, 4. And so they have the same set of solutions. Now, you might be asking, how do we go from list to a solution? What is the algorithm? And it turns out that what you can do is there's a particular form. If you put it in this form where you have lots of ones along the left, then that makes it easy to solve. And so that brings us to row echelon form and reduced row echelon form. So a matrix is in row echelon form if a row is not all zeros. So if there are any non-zero rows, then the first non-zero entry is a 1. So the first meaning the leftmost. Second, if the leading one in a row, so we know that if it's non-zero, then the first entry has to be a 1. The leading one in a row is to the right of the leading one in the row above. And this will be a bit more obvious. So basically, you want things to look sort of like a triangle going down, where you're going, things aren't going, if you have a 1 here, then you don't have anything underneath it. And lastly, every row with all zeros is at the bottom of the matrix. So we're going to move all the rows with zeros to the very bottom. And a matrix is in reduced row echelon form if in addition to do that, each column that has a 1 in the row, a leading one in the row, has all other entries in that column are 0, so even above it. So let's try this out. So I'm going to ask you, I'm going to draw a matrix, and I'm going to ask you, is it reduced row echelon, is it row echelon form, reduced row echelon form, or both A and B, or none, which is for E. So I'm resetting the thing, and let's start with this matrix. So this is a augmented matrix, 1, 2, 2, 1, 0, 0, 0, 1, 2, and 0, 0, 1, 2. The answer to Sam's question, can the leading one in the row be 2 spaces to the right? Yes, it can. But so is this, what is this? Is this in row echelon form, reduced echelon form, both A and B, or none of the above? Okay, we're starting to get a couple replies. We're getting A and E, it looks like. Getting some B's. Getting a lot of A's, actually. So people think this is in row echelon form. But, let's see. The thing here, the leading one in the row is to the right of the leading one in the row above. The leading one here isn't to the right of this leading one in the row above. And therefore, this is actually not in reduced row echelon form. So the answer here is actually E. What if I change it slightly? So So let's say I replace this here with a 0, 0. Okay, let me reset. So the answer to that previous one was E for the record. It was not in row echelon form. But I'm resetting now, and is it in row echelon form now? So I've changed it slightly. Okay, so yeah, so a lot of people think that this is now in row echelon form, and that would be correct. Yeah, so this is now in row echelon form, but it's not in reduced row echelon form because we have a 2 above the 1 here. What if I change that to a 0? Let me reset before you guys start replying. So what is it now? A, B, or C, or D? Okay, so it looks like we're getting some C's. Quite a few C's. Okay, yes, that is correct. So now it is in reduced row echelon form. Okay, and let me finish off by formalizing what we've been describing. So the process that we've been describing is something called Gauss-Jordan elimination. So it's there are 2 steps. One, the first step is Gaussian elimination. So you're using elementary row operations to convert a matrix to row echelon form. So you start from left to right. You start by using swap scales and pivots to convert the leftmost non-zero column to a 1, and 0 everywhere else in that column. Can it be reduced without being in regular row echelon form? Yes, you can, but it's usually easier to put it in row echelon form first. Like, you don't have to put it in a regular row echelon form first, but it's often easier. And so the algorithm is written this way. Then you iteratively repeat with the lower part of it. So once you've fixed a column and the row, you just don't touch it anymore, and then you work on the matrix submatrix that's to the lower right of it. And then all 0 rows can be swapped to the bottom and ignored. Note that in all 0 row, except with a non-zero right augmented term, so a term to the far right, means that the system is inconsistent, because then you're basically saying 0 is equal to 1, which is not true. And then for Gauss-Jordan elimination, what you do is you go backwards, back up. So you start with Gaussian elimination to get row echelon form, and then from the bottom right, you use pivots to 0 out the entries above it. So once you have that value, it's basically back substitution. So you're taking the value of the lower right variable, and then you're like multiplying that row by some value to 0 out the entries above it. And then you iteratively repeat all the way until you get to the top. And of course, this is a lot easier to see with an example. So let me go ahead and give an example, and that will probably be, yeah, so this example will be roughly the end of class. And I'll leave you with something for you to try out. But yeah, so let me go ahead and give you an example and try not to go too far over time. So if we have x and plus z is equal to 2, and we have 2y plus 2z is equal to 6, and minus 2x plus 2y is equal to 2, we can turn this into an augmented matrix. This is going to be 1, 0, 1, 2, 0, 2, 2, 6, minus 2, 2, 0, 2. We can convert this by taking row 3 to be equal to row 3 plus 2, 2 times row 1. That's going to give you 1, 0, 1. You didn't touch that one. 0, 2, 2, 6. We didn't touch that one. And you end up with 0, 2, 2, 6 when you do this. And now what we're going to do is we're going to take row 2 is going to be, we're going to convert it to 1/2 of row 2 because we're going to want to convert it to a pivot first. So now, note that if you're clever, you might notice that you can just directly subtract row 3 from row 2 right now. But if we're following Gaussian elimination in its entirety, what we're going to first do is convert it to something that has a leading 1, and then we're going to subtract. So you don't necessarily have to do that when you're solving the equation, but this is just to keep everything, to follow the algorithm exactly. And then the next thing we're going to do is going to take row 3 is going to be equal to row 3 minus 2 times row 2. And so this is going to give you 1, 0, 1, 0, 1, 1, 0, 0, 0, and 0, and that's 3 and a 2. And so now this here happens to be in reduced row echelon form. And it is reduced row echelon form even though you have this 1 above the other one, because it's not a leading one. So it only counts if it's the leading one. And so that means that you can convert this entire system into a new system, x plus z is equal to 2, and y plus z is equal to 3. And note that this here is an equation that is, you also have 0 is equal to 0, but we don't actually care about that, and also 0 is equal to 0. And so now this here is two equations, three variables, so infinite solutions. So before I move on, what happens if we have this thing here is going to be, if I set this equal to 3 instead. If I set that equal to 3, then you're actually going to get something slightly different. That's going to be 3. This here is going to be 5. This here is going to be 5. And this here is going to be 1. And so in that case, even though it is a correct form, that is going to be inconsistent, because that's going to have 0 is equal to 1, so inconsistent, no solutions. Okay, so all of blue here is a different example. And let's see, so I will now give you an example, which you can try out, and then that'll be the end of class. So suppose you have a Leslie matrix. Again, let's going back to the Leslie matrices, and a population vector in year 2 corresponding to 160 and 68 adults. How many adults were there in year 1? And I will stay on a little bit longer, but this is the last slide of the lecture, so if you guys have to head out now, you should feel free to. So basically, this is just an example where you guys can try it out, and I'll stay on just to, and this will all be recorded afterwards as well. So this is to solve the original problem if you have how many adults were there in year 2. And there are several different ways of solving it. You have substitution, you have Gaussian elimination, etc. Okay, so let me just go ahead and set up the problem. I know you guys are probably still working through the math right now. Oh, let me reset the polling. And so if you write this out, what you're going to get is 1, 3, 0.5, 0.9 times xy is equal to 160 and 68. And so if you write this out as equations, that's x plus 3y is equal to 160, 0.5x plus 0.9y is equal to 68, etc. But you can write this as an augmented matrix, 1, 3, 160, and 0.5, 0.9, 68. And now you just need to solve this. Okay, so it looks like we're starting to get some answers. We got an answer of D. Well, let's see what happens. So we have the first step. Let's take R2 is going to be 2 times R2. So we're just going to multiply it by 2. So that's 1, 3, 160, and 1, 1.8, 136. And let's take R2 is equal to R1 minus R2. So note that, strictly speaking, I'm combining a couple steps here, since you need to multiply R2 by minus 1 first and then add R1. But this gives you 1, 3, and this is 160, and this is 0, 1.2, 24. And the next step is going to be, you're going to take R2 is R2 divided by 1.2. And so that's going to be 1, 3, 160, and 0, 1, 20. So at this point, you've already figured out that the answer is indeed D, because you know that the second variable is equal to 20. If you wanted to, you could keep on going and reduce down and do Gauss-Jordan elimination and get R1 is R1 minus 3R2. And that leaves you with 1, 0, 100, and 0, 1, 20. Okay. Can you solve this equation instead of changing to matrices? Yes, you can, unless I tell you. So I do expect you to know how to do it with matrices, but if I don't tell you what method to use, you can use it either in equations or with matrices. So This is a technique you should learn because even though it seems really, really silly to turn it into a matrix, which seems like a lot more writing, for certain types of problems, it will make life easier. So you should learn both methods. But yeah, so well, thank you very much. Sorry I went a little bit over. Reminder that for those of you with Wednesday tutorials, your quiz is in well, about an hour. So I wish you the best of luck, and I will see you on Friday. And I will end the recording now. Bye, guys.